don't see your the current slide on this, so I'll just log in again.
When I start? Okay. Good afternoon, everyone. Myself Saankhya, and today we'll be exploring something really interesting. So, imagine a bug is stuck in the kernel for like 9 entire years. Okay? No signs at all. No broken functions, no semicolons. No missing semicolons. Just two processes happening at the wrong time. So, before we get into details, let's try to understand what read-only files are. I think it's pretty self-explanatory, right? Read-only files, you can write to them. But let's see a tiny demo. Yeah. So here, we're basically creating one of the files, and that is a mock file. This is the original file. Now we just set the permissions to read all, which is basically 444. And now as you can see, the permissions are all read all. So next what we're going to do is let's try writing into the file, which is read only right now. So of course permission is denied. Now we're actually using the exploit, which we'll speak about later. So yeah. Let's try cat. So yeah. As you can see, we've written into a read file. So how does this exactly happen, right? So it's exactly because of a race condition. So imagine two threads happening at the same time. So how do you decide which one goes first? Really depends on what gets scheduled first, right? So we have thread 1 and thread 2, and the outcome depends entirely on which one comes first. So how does Linux actually manage its memory? So each process has its own private virtual page, and of course Linux wants to optimize its space as much as possible. So mainly done it by two ways, right? One is by using page tables, other one is by using counts. So when we talk about page tables, imagine a library having millions of books. So let's say you want to access a book. So you go to the librarian, you're like, hey, give me this book. So the name of the book is going to be the virtual address. The shelf in which it's present is the physical memory, and the mapping from the librarian is the page table. Now, coming to the next one, which is cow. Let's say two students want to access the same book at the same time. So how does it actually do it? So you share the original copy for a period of time until you want to make any modifications. You want to make any modifications when new copy is made, right? So why is this done? We need to save space. So how does this exploit actually work? We use an map to map to the file. What this does, it points to the file as its pointer. Because as we saw earlier, we cannot use normal functions like let's say read or write. Because for that you would not need this. So in order to use cow, you will have to access its memory. That's why map does it. So map private basically tells the kernel, hey, you cannot write into the original file. You need to create a copy before you actually do anything. So after that is when the thread comes in. So let's say thread 1 wants to write. It doesn't clear this particular protocol or particular call. Yeah? So basically says, refer to my own memory. Instead of referring to something physical memory, refer to my own memory. I don't want to write anything. That's two parts. First, where do I actually write it, and what do I write? And this is where the problem comes in. So, the fall write. The fall write is basically something which indicates that, okay, this is something I have to write it. Now, let's say thread 2 wants to delete a page, but thread 1 already initiated the fall write. Process in fall write is first it needs to initiate a copy, after which you can write it. So your madwise is basically like tells the kernel this is what I want to do with your file. So using madwise it don't need it. Basically tells the kernel delete this memory and I don't need it. Since you've already ran fall write before this, so a copy has been created. But this madwise is going to delete the copy. But you still have to write some. So where do you write? Write originally to the file. Yeah. So as you can see, the pirate copy gets invalidated and it goes to the file. Now, from a security point of view, you can think of it like a privilege you've got root access. And of course, you can modify protected files. And one reason why this was privileged for almost 9 years, because it's very hard to trace it. Leaves behind no logs, no traces, and nothing at all. And this was exactly during when the iPhone was released, Android was born, and people used it. They exploited, I think Samsung S7 is really exploited using this, and they could access a bootloader without actually getting root access. And one more reason why they exploited for this long was because it did not. Okay, so after it was finally patched, there were still a few vulnerabilities remaining. Right? So vulnerabilities are patched, but systems still stay outdated. So for something released. So what is the problem? So even after the patch, the main thing which happened, the synchronization was reduced, right? So basically you added more number of fault rights as well as more number of flags. So that the gap between the race conditions reduces. So that is what happens. But there's still a slight chance that there might be a race condition. So people might be actively looking to exploit it, right? So at any point of time, if two race conditions are met, because it was questions.
Any questions?
Saying something about questions at 9 years of batch.
Yes. Okay.
Just repeat the
I'll
question.
just share the screen again.
Yeah, you can.
Is the question why it take 9 years to solve? Okay. So mainly because it's not easy to actually find it out, because in order to get a race condition, so two things have to go at the same time. We looked at two flags, right? So it has to happen at the same time for it to get conducted. So it has a really less probability. It can actually happen if somebody is not trying to exploit it, right? So where they actually found it was during a server tracking found by somebody called Josh in Chicago in 2016, when he was trying to look at the pings that he was getting. And that's where he found that they found an abnormality.
Should we actually go over dirty cow again? That's fine. I missed the not the demo.
That's right.
When you not that one, the next one. Yeah.
Okay.
Yeah. I think there was one.
So,
I don't remember. Could you just go over that one?
this part, okay. So let's say thread 1 starts to write. So it is going to a particular call, right? So we have blocks left man. Basically means that refer to its own memory. Why are you doing this? You don't want to use a normal function like let's say write or read. Actually you want to use count. For that you need to access the memory. And this is the easiest way to do it, since the previous thing we saw that it points to the root file, right? We have a pointer over here. So this is how you start this, right? And along with this, so explain the next part as well. Okay. So along with this, okay. So so this is where we actually indicate whether it's a write condition. So this is where it actually failed, because here the write condition is checked before it's checked right after the copy is made, before it's actually written to. So that's where the problem comes in. That is how it was solved later, by including one more fault right after it is written in.